Hey everybody. I got a request from one of our better students to do an example or two, make a video of an exercise that just sort of ties everything together. Increasing, decreasing, relative maxes and mins, concavity, points of inflection, graph the function. So that's what we're going to do with this function right here. We're going to determine the intervals on which f of x is increasing and decreasing. We're going to identify all relative maximums and relative mins. We're going to determine the intervals over which f of x is concave up and the intervals on which f of x is concave down. We're going to identify all the points of inflection. And then once we gather all that information, we're going to use that information to sketch the graph of f of x. So let's get on with it. First thing, after I erase the board, find the intervals on which f of x is increasing and decreasing. Increasing and decreasing. Where does that information come from? First derivative, right? So we compute the first derivative, and we find critical numbers. Whoops. 3x squared minus 18x minus 21. And first we look for type A critical numbers, and those are of the type where f prime of c equals 0. So we set the derivative equal to 0. And we see what that forces x to be. All terms have a common factor of 3. And since 3 is a constant, non-zero constant, I can divide both sides by 3. There we go. And if there's any justice in this world, this son of a gun is going to factor. Let's see. Looks like -7 and +1. Is that going to work? 1 times x is +1. -7 times x is -7x. X minus 7x is -6x. We have a winner. So x equals -1 and x equals 7. And remember how we got that? This is a product that equals 0. So one or the other factor has to equal 0. We set x plus 1 equal to 0. We get x equal -1. We get x minus 7 equals 0. We get x equals 7. And we have type A critical numbers. There are such things as type B critical numbers. Now, do you remember where those come from? Right. Those are the values of x that make the derivative undefined, typically because we're dividing by 0. Here's our derivative. Do we have division? going on anywhere here? We have 3 times x squared minus 18 times x minus 21. We have addition, subtraction, multiplication, exponentiation. No division. So there's no way in the world that we can divide by 0 because we're not dividing here. So type B critical numbers, none. We got our critical numbers, -1 and +7. Now let's go to our sine graph and find out where f of x is increasing and decreasing. Next step, draw a sine graph of f prime of x using the critical numbers to partition the x-axis. Here's our derivative. Here are our critical numbers, -1 and 7. And in each interval, I guess that's step 3. From each interval, select a test point to plug into the derivative. So from each of those intervals, we'll select a test point to plug into the derivative. I'll take the easy one first. 0, when we can get this as a test point, is always a good choice. Plug 0 into the derivative, we get -21. And since the derivative is equal to a negative number here at x equals 0, the derivative must be negative throughout this entire interval. We have to do the same thing with the other intervals. We just can't assume that the sign of the derivative will alternate positive, negative, positive. Doesn't always work that way. So I'll pick a test point here, and 8 would be a good test point. It lies to the right of 7. But I'll give you an even better one. 10 is pretty good. It's easy to plug in for x because we can square 10 and multiply things by 10, and it's not a difficult computation. If we plug 10 into the derivative, we get 3 times 100 is 300, minus 180 is 120, minus 21 is 91. Now the important thing is the sign of the derivative. It's positive. So on the interval from 7 to positive infinity, the derivative is positive. Now let's do the same thing in this last interval. And I'm going to try -10 as a test point. -10 squared is 100, so this is 300. Minus a -180, so that's 480 minus 29 is what? 459 or something like that. Whatever it is, it's positive, and that's the important point. Derivative greater than 0. Okay. So what does that tell us? F of x is increasing on the intervals negative infinity to negative 1 and on the interval from 7 to infinity y, because the derivative f prime of x is positive, and remember, we associate increasing and positive. That's a memory aid. And I guess here, instead of using my arrow, I'll just say also f of x is decreasing let's say from negative 1 to 7 on the x-axis, the derivative is negative, so that's where f of x is decreasing. F of x is decreasing on the interval from negative 1 to 7. And we'll note the reason why, because the derivative is negative. And remember, we associate negative with decreasing. Okay. We got increasing and decreasing in critical numbers. On to maxes and mins. Okay. We use the information that we've gathered to find the relative maxes and mins, and we do this by sketching a rough graph of f of x. And remember here, we don't care about the x and y axis. The critical numbers give us the relevant information. So we'll sketch one vertical line corresponding to x equal negative 1, the first critical number. And we'll sketch another vertical line corresponding to x equals 7. And we use these two vertical lines to partition the xy plane. To the left of x equal negative 1, what is the function doing? Wasn't it increasing? And an increasing function goes uphill from left to right. So here's f of x increasing. Okay. Between x equal negative 1 and x equals 7, on the interval from negative 1 to 7, what was f of x doing? It was decreasing, wasn't it? Going downhill from left to right. So here's f of x going downhill, decreasing from left to right between x equal negative 1 and x equals 7. Now to the right of x equals 7, from x equals 7 to from x equals 7 to infinity, what is f of x doing? It's increasing again, going uphill from left to right. Oh my goodness, how are we going to find our relative maxes and mins anyway? I got an idea. Why don't we just look at the graph and look for the high point or high points and the low point or low points, and they'll be our relative maxes and mins. Relative max at x equal negative 1, relative min 7. Now we need the y coordinates also. If I plug negative 1 in here, I'm going to get negative 1 minus 9 is negative 10, plus 21 is 11, plus 118 is what, 129? That's our relative max. And if I plug 7 in here, holy Moses, good thing I did this out ahead of time. And what did I get? It's going to be negative 127 relative min. Okay, we know where f of x is increasing and decreasing. We know what the relative max and relative min is, or what the relative maxes and mins are. Okay. Onward and upward to concavity. Concavity. First step, find the x values that either make the second derivative 0 or make the second derivative undefined. So I guess we need to compute the second derivative. The first derivative was 3x squared minus 18x, I hope, minus 21. The second derivative, we just compute the derivative of the first derivative. We'll get 6x minus 18 and a type A point of inflection. We get that from those x values that make the second derivative 0. So we set the second derivative equal to 0. Now, there's a technicality here. I can't, because of the way that point of inflection is defined, I can't automatically say, aha, point of inflection at x equal 3. What I can do is say possible point of inflection at x equal 3. I won't know for certain if we have a point of inflection at x equal 3 until I can establish that the function actually does change concavity at that point. So this is a subtle way in which critical numbers and points of inflection differ. I have a candidate for point of inflection here, but this candidate has not passed the confirmation hearings. Let's see, type B. In order to get a type B point of inflection, we have to have a value of x that makes the second derivative undefined. And typically, not always, but typically that happens when we divide by 0. We have 6 times x minus 18. We have multiplication, we have subtraction. We don't have division going on here. Ain't gonna be point of inflection. So no points of inflection here. Okay. We have our only candidate for point of inflection. What do we do now? Pretty much the same thing that we do when we're looking for critical numbers, except since points of inflection come from the second derivative, we draw a sine graph of the second derivative. Okay? We're going to determine whether x equals 3 is actually a point of inflection or not, or whether we have a point of inflection at x equals 3. The second derivative is going to have to change sign, right, at this value in order to have a point of concavity or a point of inflection. So we'll take test points, and our test points are going to be values that are easy to work with. What the heck? 10's easy to work with. Plug 10 into the second derivative, we get 60 minus 18 is 42. That's positive. So here the second derivative is positive. 0 is a good point to plug in. I plug in 0 here, we get negative 18. So every point here in this interval makes the second derivative negative. Okay. So first observation, since the second derivative does change sign at x equals 3, the point 3f of 3, and remember, a point of inflection is a point on the graph of the original function, so we get the y coordinate by plugging 3 into the original function. The point 3f of 3 is a point of inflection. And if I take 3 and plug it into the original function, let's see, what did that turn out to be? I think 1. Let's see. We have increasing, decreasing, max, min, concavity. Oops, I didn't really, I said something about the point of inflection, but I didn't really say anything about concavity here. Okay. F of x is concave up on the interval from 3 to infinity because the second derivative is positive. And the association that we want to make here, up and positive. Now, likewise, second derivative is concave down, D for down, on the interval negative infinity to 3. And why? Because the second derivative is negative on that interval. We associate up and positive, down and negative. So positive second derivative, concave up. negative second derivative, concave down. Okay, now we've got all of our information. The only thing that we haven't done is we haven't graphed the original function. And maybe it's about time that we did. We got all of our information. It's high time we drew the graph. Or as they say in the movies, we got ourselves a new courthouse. High time we had a hanging. Old movie. But anyway, we've got all of our information. Let's draw the graph of this function. And let's see. Our critical numbers were negative 1 and 7. So, we'll let x equal negative 1 and x equal 7. Tell you what, let me move that over here. X equals 7. But we'll let those be our frames of reference. Because our maxes and mins are going to occur where our critical numbers occur. And our point of inflection is going to occur at x equal 3, which is right smack dab in the middle of this. I said right smack dab in the middle of this. X equals 3. Okay. Did you ever get the impression that when I was in nursery school, I was one of those kids who couldn't color in between the lines or stay within the lines? Okay, let's see. How do I draw this now? The function is increasing from negative infinity to negative 1. And let's see. From negative infinity to 3, it's concave down. Between x equal negative 1 and 3, let's see. Increasing from negative infinity to negative 1. Okay, decreasing from negative 1 to negative 7. So decreasing here, and let's see. Increasing again from x equals 7 to infinity. Okay. Now, what have I forgotten? My concave ups, right? Concave up from 3 to infinity. Here's x equal 3. So it's concave up, concave up. Okay. I put a little note in each of these intervals saying what f of x is doing. In this interval, the function's increasing or going uphill, and it's concave down. Going up and concave down. You know what? I can do better than that. Going up and concave down. Okay. Now here, in this interval, it's still concave down, but it's decreasing. Concave down and decreasing. Okay. Now we're still decreasing or going down, but it's going to be concave up. Going down and concave up. Yeah, that didn't turn out too bad. And right here, where it changes from concave down to concave up, we have the point of inflection. X equals 3, y equals 1. Okay. Over here, increasing, going uphill, and concave up. So going uphill and concave up, fantastic. And let's see, right here at x equal -1, what happens? Relative max. Relative max at x equal -1, 129. Right here at 3, 1, point of inflection. And let's see, -1, 129, that's where we have our min. -1, -120, whoops, I'm sorry, at 1, -127. We have our relative min. And let's see, how did this become x equals 7 instead of x equals 1? I have no idea. But this is our relative min. Oh, I'm sorry. This is x equal -7. Use that. Yeah, that's right. This is x equal x equal +7. This was incorrect. Our relative min was x equals 7, 127. Sorry I didn't catch that mistake earlier. Okay, there's our graph, relative maxes, relative mins, and points of inflection. Let's see, maybe we should do one more with type B critical numbers. What do you think? And maybe this time I'll copy things down correctly. Okay, on to bigger and better things. We're going to have some type B critical numbers and points of inflection. F of x is 16/5 x to the 5/3 plus x to the 2/3 plus 2. And we're going to do exactly the same stuff that we did on the previous example. Determine the intervals over which f of x is increasing and decreasing. Find all relative maximums and relative mins. Determine the intervals over which f of x is concave up and concave down. Find all points of inflection. And finally, we're going to graph f of x. Okay, first things first, increasing and decreasing. Increasing and decreasing. The derivative, the first derivative, tells us about increasing and decreasing, as well as critical numbers. So this is the first thing that we're going to do. F prime of x. We get 16/5 times 5/3 x to the 5/3 minus 1, which is 2/3, plus 2/3 x to the 2/3 minus 1, which is -1/3. And the derivative of 2 is 0. Let's see here. Cancel, cancel. So it looks like we have 16/3 x to the 2/3 plus 2/3. And I'll tell you what, I'm going to take this x to the -1/3 and put it in the bottom. and make it x to the positive 1/3. And I'm going to have to set this to 0 and solve for x and so forth and so on. I'm going to have to work with it algebraically. So I'm going to get it in a nice form that I can work with. And the first thing I'm going to do is get a common denominator. Both denominators, well, I'll tell you what. Instead of writing 16/3 x to the 2/3, I could write 16 x to the 2/3 over 3, couldn't I? Both of these have a factor of 3 in the denominator. This also has a factor of x to the 1/3. This doesn't. So I'm going to have to multiply top and bottom here to give this expression a factor of x to the 1/3 in the bottom. So that gives me f prime of x equals, let's see. We got 3x to the 1/3 in both denominators. These two things multiply together, and when they do, the exponents add. 1/3 plus 2/3 is just 1. So these multiply together to give us 16x. And in the denominator, we have 3x to the 1/3. And we have a plus 2 in the numerator. I like this form that we've written the derivative in. We can work with it algebraically very easy now. And I'm going to erase some of the board. We've got the derivative in a form that we like. We want to find the critical numbers. And remember, type A critical numbers have the characteristic that the derivative equals 0. So we're going to set the derivative equal to 0. And see what that forces x to be. I have a quotient equal to 0. There's only one way that that can happen. The only way that we can have a quotient equal to 0 is if the numerator equals 0. Negative 2 over 16 is negative 1/8. X equal negative 1/8 is a type A critical number. We may have type B critical numbers. And the identifying characteristic of a type B critical number is essentially that it causes division by 0. Or more generally, the derivative is undefined. Here's our derivative. We're going to have division by 0 when 3x to the 1/3 is 0. Well, let's see. What's the only way that this can happen? Either 3's got to be 0 or x to the 1/3 is 0. And the cube root of what is 0? X. We have a type A critical number and a type B critical number. Well, this could be interesting. We got our critical numbers. Now we have to draw a sign graph of the derivative and find out where the derivative's positive and negative. Sign graph of f prime. Here's f prime. We use the critical numbers to partition the x-axis. X equals 0, critical number. X equals -8, critical number. And I can do this algebraically, or I can take sample points from each interval and plug them in. I guess sample points are okay. We'll use 1 as a test point. Plugging in 1 for x, we have 16 plus 2 is 18. Over 3 is 6, which is positive. So on the interval 0 to infinity, f prime is positive. In this interval, we've got to be very, very prudent as to how we choose our test value. We have to plug it in here and here. So our test value should be something that we can easily compute the cube root of. Let's see, -1/8 is -1/2 cubed. So I guess -1/3 cubed would be in here somewhere. If we cube -1/3, let's see, that's 3 cubed is 27, so that's -1/27. Okay, cube root of -1/27 is -1/3 times 3 is -1. 16 times -1/27 is -16/27 plus 2. This is a negative number, but it's less than 1, and we add it to 2. We're going to get something positive in the numerator. The denominator is negative. So what we have here is positive over negative is negative. F prime of x is negative on that interval. Okay, now that was the hairy part of this particular phase of the problem. As far as another test point, -1. That gives us -16 plus 2 is -14 on top, and -3 on the bottom. Negative over negative is positive. Bravo. So let's see. F of x is increasing on the intervals -infinity to -1/8 and why? Because f prime of x is negative. Whoops. F prime of x is positive. What am I saying? Increasing and positive F prime is also positive from 0 to infinity. So f of x is increasing on this interval as well. F of x is decreasing wherever the derivative is negative, and that happens between x equal negative 1/8 and x equals 0. And why? F of x is decreasing when the derivative is negative. And again, remember that. Increasing, positive, decreasing, negative. Okay. Now time to find our relative maxes and relative mins. Relative maxes and mins. To find the relative maxes and mins, sketch a rough graph of the original function f of x. And again, we don't rely on the x and y axes. They're not really relevant here. We have more meaningful frames of reference, namely the critical numbers. And our critical numbers are what? Negative 8, negative 1/8. And x equals 0. And we know that from negative infinity to negative 1/8 on the x-axis, f of x is increasing. So to the left of x equal 1/8, f of x is increasing, which means it goes uphill. Between x equal negative 1/8 and x equals 0, f of x is decreasing, so it's going to go downhill from left to right. And then from x equals 0 to x equal infinity, f of x is going to be what? Increasing? Yes, increasing, going uphill. Now, I don't know if I have the concavity right here. Maybe, maybe not. But the important thing is I've found the high and low points of the graph. This is negative 1/8, f of negative 1/8, which is a relative max. This is 0, f of 0. Relative min. Okay, now let's see if I can actually compute what these are. This is probably not going to be a problem. 0, f of 0. And what was f of x? 16/5 x to the 5/3 plus x to the 2/3 plus 2. Okay. So let's see. 0, f of 0 is 0, 2. Now, will the relative max be as easy to compute? Let's see. Negative 1/8 f of negative 1/8. And I hope this turns out simpler than it seems. F of negative 1/8. I'm going to get 16/5 x to the 5/3 plus x to the 2/3 plus 2. You know what? Because negative 1/8 is a perfect cube, we can do this. To compute negative 1/8 to the 5/3, we take the cube root and then raise it to the 5th power. The cube root of negative 1/8 is negative 1/2. And we raise that to the 5th power, that's negative 1/32. So we're going to have 16/5 times negative 1/32. Okay, and here, to compute negative 1/8 to the 2/3, we compute the cube root of negative 1/8, which is negative 1/2, and then we square it, which is positive 1/4. Now, let's see. 16 over negative 32 is negative 1/2 times 5 is negative 1/10. Plus, let me see now. Am I missing? I'm missing something, I think. Hold on just a second. I got it. For some reason or other, I was thinking these were multiplied together. Negative 1/10 plus 1/4. Okay, this is negative 2/20 plus 5/20 is positive 3/20 plus 2. Positive 3/20 plus 2. 2 is 40 over 20. 3/20 plus 40/20 is 43/20. Okay. Negative 2/20 plus 5/20 is 3/20 plus 40/20 is 43/20. Good gravy. This is our relative max. And this is our relative min. We'll record that. 0.2 is relative min. Negative 1/8, 43/20 is relative max. And thank goodness we're done with this part of it. Now we just go on to concavity and points of inflection, and hopefully those will be more manageable. To get f double prime, let's recall our original function. We compute the derivative, and the 5's cancel here. We get 16/3 x to the 2/3, 2/3 x to the negative 1/3. We compute the derivative again. 2/3 times 16/3 is 32/9. Subtract 1 from the exponent, we get x to the negative 1/3. The derivative of 2/3 x to the negative 1/3 is negative 1/3 times 2/3 is negative 2/9. Subtract 1 from the exponent, we get negative 4/3. This is the second derivative. But again, we want to get it in a form that's easy to work with algebraically. So I'm going to take the 32 and put it on top, put the 9 on the bottom, and the x to the 1/3, I'm going to move that down to the bottom and make the exponent positive. And I'm going to do something similar here. I'll keep the 2 up top, keep the 9 on the bottom, and bring the x to the negative 4/3 down to the denominator and make the exponent positive. And I want to combine these two terms. The denominators both have a factor of 9. This has a factor of x to the 4/3. This has a factor of x to the 1/3. How do we get this from this? If we multiply x to the 1/3 by x, which is the same as x to the 3/3, we get x to the 4/3. So I'm going to multiply top and bottom here by x. And now my denominator is 9x to the 4/3. Okay, let me clear a little space. Here's our second derivative simplified. And we're going to find our candidates for points of inflection. A type A point of inflection is a point of inflection where the derivative is 0. We have a quotient equal to 0. That only happens when the numerator is 0. Two over 32, which is 1/16. This is a candidate for a type A point of inflection. Now let's find type B. Note that our second derivative is undefined exactly when the denominator is 0. This happens when the denominator is 0. What real number, when we raise it to the 4/3 power, is 0? Gotta be 0. One 1/16 and x equals 0 are candidates for points of inflection. We won't really know for sure until we check and see whether the concavity changes at these x values.